Actually starting the lesson. I told you we are going to be, this lesson will take the full class. We got a lot to go through. Doesn't look like it, but we do have a lot to go through. Because when I teach, I not only teach what the current standard is, but I also go back to things you should know from previous that will help you with what you need for this class. So first, write or construct balanced chemical equations. We've actually already done most of this, haven't we? Single replacement, combination, decomposition, double replacement, combustion. You should put a check mark there because we did most of that last class. We still have one more to go over, but I'm saving it for Friday right before the lab because it's going to be the type of lab we do. 1.5, perform calculations with the mole concept, including volumes. Anybody know what a volume is? What's a volume? Volumes and concentration. You're talking about gas volumes. Volumes of solutions, right? Look at the amount of liquid you have, right? So we would be looking at our beaker in this case. So we've learned it in the past as liters, milliliters. We're going to use a slightly different unit you'll see today, but we have to go through calculations for molarity, basically. We're going over molarity today. And then we're going to be looking at something called solubility. Does anybody remember solubility? If something dissolves in water or not. So we'll be going over the solubility rules. And then they specifically want us to memorize the variation in solubilities of hydroxides and sulfates. This is going to be a periodic trend, believe it or not. Periodic trend here. Or trend alert. More periodic trends. Add it to your charts. We actually had one last class. For those of you who weren't here and those of you who may have forgot, what was the trend we learned last class? There was another trend last class in thermal decomposition. As you go down for group 2, the energy required to decompose increases, right? We learned that last class. Yet another trend. You can expect your quarterly is going to have a lot of trends, ionization energy, all of that stuff that we learned in unit 1, unit 2. There's a lot of trends. Still have more trends. All of these trends are with group 2, by the way. More trends. Add to your periodic tables. All right. Periodic trends, energy required increases to decompose. So that means that, for example, it requires a lot more energy to decompose barium carbonate than to decompose magnesium carbonate. That's what that means. Okay, so here we go. First thing is kind of a new topic. I don't remember how much I covered it with previous last year. I know the year before I definitely had went over it more. But I think we did go over dissociation when we were learning about acids and bases. So one of the basic ideas, in acids and bases and in salts in general is when we take an ionic compound and we throw it in water, it breaks up in water. Is that something that sounds familiar? I take an ionic compound, I put it in water, and it breaks apart in water. Another word for that is called dissociation. And so the actual literal process of putting salt in water is that the Na+ ions will separate from the Cl- ions. And what separates the Na+ from the Cl-? Water. So water actually surrounds the positive ion, and water surrounds the negative ion. And so really all that you have to remember is that your ionic compounds, they break apart when placed in water. They don't always break apart though. Do you remember something called soluble salts versus insoluble salts? If you do a chemical reaction and you see a solid form at the bottom of a solution, we call this a precipitate. Another way of observing a precipitate when you're doing the reaction is your mixture stays cloudy. You don't see everything dissolved. Whereas if everything dissolves, you have a colorless mixture, we call this soluble. You hear that? That's the roof. They're working on the roof. This sounded like rolling at one point. They must be rolling something on the roof. All right. If you have a precipitation reaction and you have some ions that aren't doing anything, we call those spectator ions. Have you ever heard of a spectator in a sport? Like you're watching the football game on the side or basketball game. Spectators are like the people on the sidelines, but they're actually not scoring. They're not hitting the bat, doing the baskets or whatever it is you do in sports, making the touchdowns. The spectators are on the side. Spectator ions actually don't participate in a chemical reaction. They're just chilling there in the solution. They're around, but they don't form the precipitate. And so that's important to note this terminology. Spectators are just watching. They're in the solution, they're just watching. And we're gonna look at spectator ions a little bit more later on. That's my eyes going to the side. They're there, they're watching, but they're actually not participating in the chemical reaction. So before we move forward, let's practice ionization. Do you know how to ionize ionic compounds in water? What would the ionization for barium hydroxide look like? What happens when barium hydroxide is placed in water? How do we write that out in chemical equation form? Go ahead. Right. So first thing you got to do is you got to separate your ions. You separate them with a plus. So you know you've got barium, and what's the other one here? Barium being separated from hydroxide. Oh boy, but what are the charges? What are the charges? Barium is +2. Hydroxide is -1. And what else do I gotta do? There's two more things. They're in water. So states are gonna be dissolved in water. So you write aqueous. One more thing to do. What's the last part?
Balance.
Which means whatever is outside the parentheses or at the bottom here comes to the front. What this is saying, if you were to look at it in picture form, is that if I throw barium hydroxide in water, I have barium ions floating around, and I've got hydroxide ions floating around, and I've got double the amount of hydroxide ions floating around than I've got barium ions. Does this ring a bell? All right, Na2CO3. Let's try this again. Yes. When the money gets back. Let's try this again. What's my first ion? My second ion. And how do we know the charge of carbonate? What's something that can help us here?
The amount of sodium.
Yeah, because remember, you can cross the amounts to become the charges. So if I've got 2 sodiums, that means the charge of carbonate must be 2 minus. So CO3 minus 2. Is it balanced?
No.
And last thing, what I got to do? Wait. AQ. AQ. This is basically saying when sodium carbonate is placed in water, it's going to break apart. It's going to be soluble. Kind of, maybe. Something familiar. Never seen it before in your life. That's okay. You'll be dissolving something in a little bit. Very exciting, I know. All right, we're going to continue. So, example of ionic equations. The next thing you need to be aware of now is whenever you see an ionic compound that says AQ, what does that actually mean about that ionic compound? It's actually dissolved in water. It's actually broken apart into its ions. So how do we then read this? Zinc, which is a solid, When it is placed in a solution of copper sulfate, the single replacement reaction occurs. And what actually happens here? We said last class that in a single replacement reaction, that one element would replace another element. So what does that actually mean? Zinc kicks out copper, right? Zinc kicks out copper. Goodbye, copper. You see copper at the end. Is the color of zinc and copper different? Yeah. So you actually observe this, and I do this as one of the reactions in pre-age chem that we do in one of the labs. You would observe copper is like a brownish that forms out of the solution, and you end up with zinc sulfate. So I have a question for you. Does sulfate do anything here? Sulfate does absolutely nothing. It starts dissolved in water and it ends dissolved in water. So what does that tell us about sulfate actually? It's called a spectator. So sulfate, because it starts dissolved in water and it ends dissolved in water, this is what we call a spectator. It's there, it's not doing anything. That's the truth. It's present, but it's actually not part of the reaction. And so what you have to learn, and what I'm teaching you in the first standard, is if Cambridge asks you to write an ionic equation, what this means is you do not write spectator ions. You actually cancel out spectator ions. So ionic equations only involve the actual replacement that's taking place or the actual solid that's being formed. So what's actually changing in the reaction. So it means spectator ions are not included in what we call the ionic equation. In this course, where you're going to see this standard is mostly in paper 3. You're actually going to do a reaction. They're going to say write out the ionic equation for this reaction. And so we'll be getting practice with that, of course. But I just want to tell you that that's what this is. So this is actually the final equation for the same reaction, taking the sulfate out, saying that zinc and copper switch places. Can you tell by looking at this if this is another specific type of reaction besides single replacement? Notice zinc goes from having a charge of 0 to a charge of +2. Copper goes from +2 to 0. Is that a type of reaction we may have studied in the past? If the charge changes.
Ionization?
Ionization is redox. This is redox. I've warned you, redox is coming. This is not the lesson for today, but redox is on its way. It's coming within a couple of weeks. Your second titration lab will be a redox titration. What does redox mean?
It's the opposite of ox.
It means there's transfer of.
The opposite of oxidation.
That's reduction. But redox itself means that in this specific reaction, there's a transfer of electrons. Some chemical reactions are redox. Some of them are not redox. Yes. After Alina gets back, you'll be next. All right, so you may want to make that note. Every time redox is hinted at, I'm hinting it for you. It's on its way. It's coming. It's in this unit. It's later on in this unit of study. Within a couple of weeks. All right, but we're in ionic equations now. So let's take a look at what we need to do. What type of questions could we be asked here? Change these full equations to ionic equations. So what are you being asked to do? If you are being asked to construct an ionic equation. No spectators. How do you know what your spectator ions are by looking at this? So can you figure that out just by looking at the equation? How would we go about this? What is a way we could go about this? Go ahead, Nikki.
Is plus something that changes its liquid.
So we should ionize all of our aqueous reactants and all of our aqueous products. So step one, what you should do, and once you get the hang of it, you may not have to do step one, but let's just do it to get the understanding. Step one would be to ionize all AQ compounds. What do I mean by that? Ionize all AQ compounds. Write them split apart. The same way that I did right here. We need to do this for every reactant and every product. So ionize all aqueous compounds, meaning that show all the compounds that are dissolved in water. So H2SO4 is dissolved in water. How is that dissolved in water? What are the ions in H2SO4? What are those ions? They would be 2H plus and SO4 minus 2. Pause for a second, does that make sense? Because this is the positive ion, this is the negative ion. You've got 2 hydrogens, so that has to go to the front, right? You've got 1 sulfate with a negative 2 charge. Does this make sense as the ionization of the first one? Does NaOH get ionized? It's AQ. Does it break apart in water? Anything that's AQ breaks apart in water. So this is, for NaOH, let's do it again, 2Na plus 2OH minus. Does it make sense that I distributed the 2? Does this make sense? The other reactant that I ionized. Let's look at the product side. If I have a compound that's not aqueous, do I split it up? No. So we would leave water together. 2H2O, liquid. So only break up your aqueous compounds. This is what I said earlier. Water is not aqueous. Water does not dissolve in water. Water is water. Water stays together. Na2SO4, how would that break apart? Next for the bathroom. Did you need to go? Okay, so how do I break this up? 2Na plus and SO4 minus 2. That's step one. Break up all of your ions that are aqueous. Make sure you have it written down. Step two, cancel out spectators. Can you look at any ions that are the same on the reactant and the product side? Do you see any that are the same? What are they? What's our spectators in this reaction? What's actually not reacting? It's not reacting if it's the same on the reactant side as it is on the product side. So sodium is like, you know, it's there, it's just watching. Just watching, it's a spectator. Sulfate is just there, just watching, right? So you cancel it out. And so write what's left. Step 3, write what's left. So what's the actual reaction? 2H plus 2OH minus goes to 2 waters. And this is the official method to get an ionic equation. Now, as always, if I can make this easier, I will, and I am about to. I wanted to go through step 1 so you understand what a spectator is. Do we have an idea of what a spectator is? It's present in the solution, but if it is the same exact ion in the beginning as it is in the end, and there's no change in state, Like it's not changing solid, liquid, gas. There's no change in electrons. The charge hasn't changed at all. Is Na plus, for example, actually reacting, or is it just chilling? Just chilling. It's just there, right? And so an ionic equation only shows the reaction taking place. So what's the actual reaction taking place here? What's H plus? Anybody remember? What is H plus? pH is based off of H plus. What's H plus?
Hi.
pH scale based off of H plus. What is H plus?
Neutral?
It's an acid, right?
Good.
Acid plus what's OH minus? OH minus is not an acid. OH minus is a. So the actual reaction that's happening is acid plus base go to water. If you want to neutralize an acid, what do you add? Base, because you make water, right? That's the actual reaction that's happening. Just want to bring that up because remember, next class we're doing an acid-base titration. So we're going to have two compounds like this that are reacting together. And you could be asked for the ionic equation, actually. So you've got to make sure you're taking this lesson into account. A lot of this lesson shows up on paper 3, which is the lab. All right. So what if I told you there was an easier way? Thank you. How long will they be in my room? 15? Okay. We're planning on having them do elements in case, like having them create it. Yes, like them do these girls. That's the goal. You're welcome. Getting ready for magnet show day. All right. Can we make this easier? Because this seems like a lot of work. I don't want to write that much. You don't want to write that much. So is there a way we could make this simpler? Anybody see anything that we could have just done? Anything we could have done to have made our lives a little bit simpler here? Look at the product side. Look at what's not aqueous. That's the reaction, right? That's the thing that's happening. So if you remember, oh, we're making water. You can remember, oh, what are the ions that make up water? H plus N, OH minus. And there's the reaction. And so let's go ahead and, for this question, yeah, let's try it. Let's see if we can do this one a little bit quicker. Change this full equation into an ionic equation. Can you identify the spectator? So let's try this a quicker way. Identify the spectator. What's just watching? What's not doing anything on the reactants to the product side? Good guess, but no sulfur in this reaction. What's the spectator? Potassium. Why? Bromine goes from liquid to aqueous. So something's changing. Potassium starts aqueous and ends aqueous. It starts in water, it ends in water. Like a couch potato, it's just like it didn't move. It's just there, right? So let's see if we can maximize our ideas here. So then if we just know to take that out, what will we have to write as our answer? How would we write our final answer, knowing that we take out the spectator? What would our final answer look like? Br2L. And here's where you have to be careful if you use the shortcut method. How is iodine supposed to be written in an ionic compound? The standard state. Right? So this is where I thought you might come into issues if you skip that step and do the shortcut method. You've got to recognize that this is a positive ion and this is a negative ion. So when you write iodine, you have to write it as iodine as it is in the solution, I minus. And how many of them are there? And you can't forget that. You didn't cross out the 2, you crossed out the potassium. So make sure you're taking out just the spectator. 2I minus. Let it marinate. Does that make sense? Product side. What did I take out? Potassium. So what would be written here? If potassium is plus, then Br must be minus. So it would be 2Br minus. And the other thing is? The potassium doesn't change. It's just chilling. What changed is bromine went to Br minus and I minus went to I2. That's the changes that occurred. So when you write the ionic equation, you are only writing the atoms or ions that change in a chemical reaction. You take out the rest. So you take out what we call the spectator ions, anything that stays the same at the beginning and end of the chemical reaction. All right. See if you can use the trick for this one. This is actually, for these types of reactions, the trick's going to be really helpful for you. Can you identify what happens in this reaction? What's happening? It's a double replacement. And what's the change that's occurring? Look at the states. You make a You make a PPT. What's a PPT? PPT is shorthand for precipitate, which means that when you mix these 2 liquids together, you get a solid at the bottom. When you mix the 2 liquids together, the 2 solutions together, you get a solid at the bottom. Yes? It's a spectator. And there's another one. How can you identify the spectators real quick? It repeats on both sides. It's this other compound. So your spectators here should be sulfate and sodium. So the quick way to do this is recognize what's happening. You're making the solid. What are the ions that come together to make that? And copper has what charge?
So as long as they're being
Same way.
they have to have the same state, the same.
Same state, same charge spectator. If the state of matter changes, or if the charge changes, they're part of the reaction. Because the chemical reaction is either some kind of change in state of matter, or it is a transfer of electrons, if it's redox. And so what we're looking here is that all of this stuff is dissolved in water, but 2 of these ions come together to form this solid. This right here is a precipitate. We are only showing, so it's almost like a reverse ionization, right? If you think about it, it's like a reverse ionization. Yes?
Does copper always have a charge?
That's a great question. The answer is no. But how would we know that it's +2 here? Right, you could look at this. Hydroxide is -1, but there's 2 of them, which means that this is positive and the 2 is there. So you basically just do the reverse crisscross thing, and that proves why it's +2. You could have also got it on the reaction side. Sulfate's -2, so copper must be +2 because there's 1 of each of them. But you would have to know that SO4 is -2 in order to get that. Which means you've memorized your polyatomic ions. Yes. Yeah. Why? Because those ions are aqueous on both sides of the chemical reaction. So anything that's the same on both sides of the chemical reaction is considered a spectator ion, so they would not be included in what we call the ionic equation. And the purpose of the ionic equation is to simplify the reaction to say what's actually going on, what's being observed. In this reaction, what's being observed, you mix these 2 solutions together, you make a solid. Well, what's the solid? It's this, copper hydroxide. Because basically getting out all the other stuff that's going on. The actual reaction that's happening is copper is combining with OH minus to make a solid. Yes.
So if we weren't putting an ionic equation, there would be a double reaction.
The regular double replacement.
So
So this is just to show what happens, simplified almost, like a simplified chemical reaction that shows just what is happening. All right, so, here we go. About to get to what I was going to talk about. I have bad news. Good news, bad news? I don't know which one to tell you. Does it smell? Does it smell? I like that. Does it smell? Have you ever heard of the solubility rules? Do you know what solubility is? What does soluble mean? Soluble means dissolves in water, right? You may want to write this down just in case you forgot or never learned this. Soluble means dissolves in water. Insoluble means doesn't dissolve in water. So what about copper hydroxide here? Copper 2 hydroxide, is that soluble or insoluble? What do we think? Insoluble, right? This is an example of something that's insoluble because it's going to make a solid at the bottom. You're not going to be able to dissolve it. So I bet you were wondering what I was doing with those beakers. I have a selection of ionic compounds for you today. We're going to be looking at the solubility rules. And so, what's the bad news? They have to be memorized. What's the good news? I have an acronym to memorize it pretty quickly. But yeah, they have to be memorized. And so the list grows. What's the other part of the good news? It's not really that great. Does it smell? Not really. Ionic compounds don't smell. Does salt smell? Ionic compounds don't smell. All right, here they are. Which one? Salt. Oh yeah, some of them do. Oh, maybe, depending. Like the ocean has some kind of salty smell. There's just some smell, but it's not like strong smell. Organics usually are quite smelly when we get to organic. Ions that are generally soluble in water. This needs to be memorized. And guess what it ties back into? Solubility. Polyatomic ions. So, all group 1 metals are soluble in water always. That's the main rule. If you don't memorize anything else in solubility rules, memorize if there's a group 1 metal, it's going to dissolve in water. Every time. If I see Na, or lithium, or potassium, or rubidium, or cesium, you can guarantee you throw that in water, it will dissolve. 100% every time. So group 1 always dissolves. That's the most important one to remember. That means it's always going to be aqueous. So dissolves is aqueous, right? Doesn't dissolve as solid. Ammonium compounds dissolve. So I've got the first one here. I've got some ammonium chloride for you. Anybody want to test ammonium chloride if it dissolves in water? 1 table. All right, Hakeem, you had your hand up first. So I'm giving you NH4Cl. NH4Cl has no bonus in here. What did it say at the front? All right, you can dissolve it. Put it in water and stir it. All right, another table is getting a different one. So we're gonna hold on to this here. Nitrates always dissolve in water. Chlorates always dissolve in water. Sulfates, chloride. Before we go on, let me get your attention. There are exceptions here. Most of these, I've never seen Cambridge test except for one. So I want you to circle that one. Silver chloride, you must memorize, is insoluble. That's the only exception that I've seen Cambridge actually test, and it shows up in a standard later on in the class. So the rest of these exceptions, just be aware of. We'll talk about some of this stuff later, but I'm going to try to give you as simple of a version of the solubility rules to memorize as possible, and this is it. Glands. What does that mean? I made this up. It's a mislead patented design acronym. S stands for soluble, and then Cl stands for chlorine and chlorate. A stands for ammonium and alkali, which is group 1. N stands for nitrate, and S stands for sulfate. S, glands. Glands. Soluble is chlorine-based compounds, or the S glands. Ammonium, alkali metals, nitrates, and sulfate. The sulfates, these two also we're going to have to look at. Those two are important. Cl, ClO3 minus, that's chlorine and chlorate. Ammonium, alkali, nitrates, and sulfates. Glands. All right, let me see if I got another one of these glands to show you. I've got here some barium chloride. Who wants barium chloride? I saw Rosalind's hand up first. You've got some barium chloride. Yes. I don't have to, but I need to buy some. I need to buy some. I know this. Oh, we're doing. I'm putting the water. All right. Next, calcium chloride. Calcium chloride. So this group with their hands up. Hold on. Yes. Yeah. Calcium chloride. Just when you get it, put it into the beaker. There you go. Got some calcium chloride. We'll leave it here. All right. Nitrate. Anybody want to test the nitrate? Is that your hand up first? Yeah, just dump it. Dump it.
Yeah.
Go ahead and dissolve it in water. Try not to touch that. Yeah, throw it in the water and dissolve it. All right. I have now. I have one more chloride. Which of you wants this? All right, here you go. You've got sodium chloride. You've got table salt. So, can you dissolve that?
Doesn't everyone else like crunching on their water?
All right, throw it in the water, dissolve it. Does it dissolve? Okay, so I've got a few more. I've got a sulfate. Anybody want to try a sulfate? This is for your group. This is magnesium sulfate. It has a name called Epsom salt, but you'll see that it's magnesium sulfate. You can pour some in and dissolve it. All right, I got a few more. I have calcium carbonate.
That was you, not me.
All right. So, pour a little bit in. Pour a little bit in.
Do you think it would be salty?
Here.
Alright.
Yeah, I will.
Oh.
All right. Dissolve, 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 dissolve. Dissolve, 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 dissolve. Throw it in. Yeah, keep it Okay, so let's take a look around the room. Yeah, you overdid it, but oh, you added too much. Okay, so everybody stop stirring at this time. I want to gather your attention. Let's take a look. Stop stirring at this time. You now can't make your observation. That's cool though. All right, so if you have chloride, did it dissolve in water? Nitrate, did it dissolve? Nitrate, right? Did that dissolve in water? Is that clear, see-through? Even though it's blue, you can see through it. You don't see precipitate, right? All right. I see a couple solutions that have, this is what we call thick. This is thick, right? Can you see through this? If you can't see through this, that means you have a precipitate. It is a cloudy mixture, you have a precipitate. And so when you are analyzing labs later on, this actually means precipitate, whereas Roslyn, for example, definitely no precipitate there. You couldn't even tell that apart from water, could you? But there's barium in there. No, not tasty. All right, so no. I also have that group right there, Diane and Kat. Look at your solution. Hold it up. It's not dangerous. What does it look like? For real, right? Can you see through it? Not really. We would say that's precipitate.
Wait, what is it?
What was your compound? What was your compound? All right, so proof, solubility rules. You need to memorize. Your insoluble salts are carbonates, hydroxide with some exceptions, oxide, and phosphate. And I made a acronym for this. This is a Miss Lead special. I chop. Insoluble is carbonates, right? Carbonates, hydroxides, oxides, and phosphates. So it gives you the first letter. I chop. So if I'm looking for insoluble, carbonates, hydroxides, oxides, or phosphates. Now what about exceptions? Is there any positive ions I could put with an insoluble ion that would make it soluble? Is there anything I could put with a carbonate that will be soluble? Let's have Sophia check. Since Sophia was out in the bathroom. Well, that means you, last but not least. That's what I got here. I got some sodium carbonate. Let's see what happens. Give me back my dollar. Stir it up. All right. Exception. Write this down. Remember the first thing I told you, the very first thing to remember. If you don't remember anything else, you don't remember my acronyms, you don't remember the exercises, you don't remember the practice, please memorize group 1 metals are always soluble. If a group 1 metal is with a carbonate, it is actually soluble. If a group 1 metal is with a hydroxide, it is soluble. If a group 1 metal is with an oxide, it is soluble. If a group 1 metal is with a phosphate, it's also soluble. But when other metals are with these, they are insoluble. That's the way to understand it. Kind of makes sense? So soluble glands, and then insoluble chop. I chop. That gives you what you need. Now, do you need to memorize those polyatomic ions? Yeah. Absolutely. This also feeds into knowing your polyatomic ions. But this demonstration was just to prove to you carbonates are not soluble. I can throw any carbonate in water except for sodium carbonate. Did this dissolve, Sophia? Oh, it dissolved! So sodium group 1 metal dissolved. Group 2 copper did not dissolve. All right. So that's something important. You've got to memorize it. It feeds mainly into paper 3. Most of what I'm teaching you today mainly shows up on paper 3, which is the lab paper. So most questions in this topic are paper 3. Why would it be paper 3 that this would be tested? Lab. This is all lab work. All right. There is some specifics, periodic trends, more trends to know. Cambridge specifically, and for a reason I do not know, wants you to know the solubility of 2 different polyatomic ions going down group 2. So down group 2, this is what you need to memorize. The solubility of hydroxides increases down the group. Meaning, the most soluble hydroxide down group 2 would be what? If solubility increases down the group, the most soluble hydroxide is? Group 2, group 2.
Oh, radium.
Radium, but radium's radioactive, so you're not actually going to see it, so it would actually, in practice, be? Barium. And what I want you to memorize is that the solubility for hydroxides and sulfates is exactly the opposite. So if the solubility of hydroxides increases down the group, this actually means the solubility of sulfates increases up the group. So this is something you need to memorize. Why is beyond the scope of this class, and they do not want you to know it's complicated. We just did it in A level. It is a complicated topic. You don't have to know why. You just have to know at this level that this is a trend, that this happens. So if I have magnesium sulfate, oh, didn't the group have magnesium sulfate? Who had some Epsom salt? Did that dissolve? Yeah. And where's magnesium? Is that up the periodic table or down? Up. So the solubility of sulfates is more likely to be soluble the farther up you are in group 2. Kind of makes sense? This needs to be memorized. So write it down the way that I did it. I usually like to do arrows, so I put a lot of information in a little bit of space when I'm studying. We're good with this? Here's the type of question. Let's take a look at the question. In which row of the periodic table are all statements comparing the compounds of magnesium and barium correct? So looking at what I just taught you, that's standard. Can you predict the solubility? Which would be more soluble, magnesium hydroxide or barium hydroxide? Go ahead.
C.
Oh, okay. Yeah, but to answer my question. Barium, right? So it's either C or D. And then sulfate, which one's more soluble, magnesium sulfate or barium sulfate? Right. So remember, hydroxides is down, sulfates is up, the periodic table. So here we would be looking at the answer to be magnesium. So the correct answer for both is C. How quickly could this be solved on a Cambridge exam? You knew what you were reading. 30 seconds, right?
3.2 seconds.
Is this worth less points than the question I showed you in the bell word?
No.
It's worth the same. That's what I was saying. That's what I was telling you. Go for the easy marks first. But you've got to memorize this to know the answer. You either know it or you don't know it. Paper 1 is multiple choice. 2 written, 3 lab. All right. Another way of looking at it. This one's a little bit more complicated. Yeah, it's 2, 1, 3. Oh no, 2, 3, 1.
So the lab is
You take. Be careful,
No, no,
David.
no.
I need you to sit your chair.
He's
No,
talking
I'm
about the
gonna
points. He's talking about the points, like how much points each is worth.
2, 1, 3. All right, so let's take a look at this one. You've got 2 solutions. I need everybody's attention. One contains Mg plus, the other contains Ba2 plus. They give you sodium sulfate being added to in test 1, sodium hydroxide being added in test 2. This is another way they could ask you the same question, it just looks a little bit different. Test 1, that's adding Na2SO4. Test 2 is adding NaOH. Would Na2SO4 give you more precipitate, solid, with barium or magnesium? So what does that mean? Precipitate, what is that?
less salt.
Less soluble, right? More precipitate means less soluble. So with sulfate, is barium sulfate less soluble or is magnesium sulfate less soluble? Let's trace the trend again, right? We said that hydroxides increase this way, sulfates increase this way. So where would be less soluble for sulfates? We said more soluble is this way, so less soluble is down, right? So more precipitate with barium. And what about NaOH? Which one is less soluble with hydroxide?
The other way around?
The opposite, right? Just memorize they're the opposite. And so
And
it would
it's
be
only for hydroxide.
hydroxides and sulfates. And it's within the same standard, so they want them memorized together. And so it's like that. Because when you add Mg2 plus to NaOH, you get more precipitate. Barium hydroxide is more soluble, so less precipitate. That's another way of almost asking the exact same question. Now, we still have some work to do before we leave for the day. You have not seen the math yet. So we have some math to get through before we leave for the day. Yes, we're about to learn. CM cubed, you mean? We're about to learn. That's what's coming right now. So, units in this course. Because this is an international course, not an American course, we actually no longer ever use milliliters or liters. So anytime you see milliliters, you need to transfer it in your head and instead rewrite it as centimeters cubed. This takes effect of the fact that volume is length times width times height. That's how we come up with it. Centimeters times centimeters times centimeters is centimeters cubed. That's actually 1 milliliter. Liters are now known as decimeters cubed. What does that mean? You've got some beakers in front of you. So all of our beakers are going to be written with American units. So this says 400 milliliters at the top, but now in your head, what do you need to read that as? Centimeters cubed. So every time you see ml, it's the same thing as centimeters cubed. Yes? Grab a cup. And this is a conversion you can memorize. It's actually the same thing I taught you a few weeks ago. When you move your decimal over one spot between centi and deci, you may remember King Henry died unusually drinking chocolate milk in the first lesson. I told you if you moved over once, but you had something that was cubed, you actually move over 3 times. Do you remember that? No?
Yes.
So every move of 1 is actually a move of 3. We're going to see that in questions shortly. If you don't remember that, the other conversion is this one. You can memorize 1,000 centimeters cubed is always equal to 1 decimeters cubed, and it tells you the same exact thing as what I did with moving the decimal over. There's more than one way to solve the question. The other thing you need to remember is the following. We are going to be looking at concentration in only one unit. The only unit we care about is molarity in this class. Do you remember molarity from previous or honors? We would have learned in previous or honors chemistry that molarity is moles over liters. Mole liter, molarity. That's what we would have learned there. And given the volume and given the moles of any substance, we would divide the two, we get the concentration. That's how much there is of solute in a given solution. Well, now you need to know that molarity is the only concentration unit that Cambridge cares about. There are other concentration units, but molarity is the only one that Cambridge ever tests. Mole stays the same. That's still there. But every time I see liters, that's now. So the way we would understand this is concentration is moles over dm cubed. And it's a formula, and you should memorize this formula in the way that it's written here. Moles over dm cubed. Now, those of you who love math, or maybe you don't at the moment, but in general you like math. If I see a variable at the bottom, can I bring it to the top?
Yes.
Like if I have 1 over x to the second, what does that mean? If I brought this x to the 2 to the top of the x, like fraction bar, what would that be? It would be x to the minus 2. Does that ring a bell? So mole over dm cubed is the same thing as mole dm. Moving this to the top, you change the exponent from positive to negative. And your question, what's that? That's the answer. This is concentration in molarity. They've given you molarity there. How concentrated your solution is. That's what that stands for. Good? Make sense? It's a little weird. You're gonna have to get used to it. But these are the units we're gonna use, and we're gonna use them in the lab next class. So that's why I'm teaching it to you. Moles dm cubed can show up as moles dm minus 3. Whenever you see this, that's concentration. What's being told to you is the concentration. Now, I would memorize the formula this way. Because you're going to be given concentration in moles, or you're going to be given concentration in volume, and you have to solve for something that's missing. Yes?
So how does 22.4 say?
22.4 is not involved, because that's gases. When we use 22.4, that was for gases. That's another lesson for another day. Solutions don't involve 22.4. All right.
But it's still used.
It is used for gas volumes.
So it's just instead of liters, just put
dm cubed is there too. Yes, that would relate that way. All right, in the lab you do next class. The first thing you're going to have to do is prepare a solution. When you do a lab next class, you're going to prepare a solution. You're going to use this piece of equipment. It's called a volumetric flask. It has one job, if you did or didn't forget. It can measure only one volume by getting your volume exactly to this line. There will be a line that's printed. You have to match that line. Do you remember what happens if you go over?
Yeah, start over.
You start over, right? I'm telling you what's going to happen next class. So the first step of what you're going to do next class is you're going to prepare a solution. And you have to make sure when you prepare that solution, your meniscus, which is the bottom of the curve, meets that line. You have to show it to me that you got it right before you can move forward. you just are like, well, I'm just gonna pour some out and get to that line. Guess what you've messed up? If you take some out, if you go over this line and you take some out, what have you messed up?
Now there's liquid in the.
When you take out the liquid to go back down, you take out some solute as well, so you change the concentration. You change the amount of moles of what you have in there, and you're gonna mess up your accuracy. The short story is you're gonna mess up your accuracy. So you have to get to this line as the first step of creating a solution. Yes. I do. Give me a moment. All right. So we use these volumetric flasks that measure 250 milliliters. How do we read 250 milliliters now?
250
dm cubed. So write that down. Because on a Cambridge test, they're not going to use milliliters, but our equipment is going to. The equipment we have measures in milliliters. So you've got to be able to recognize the unit difference. All right. This is something that is not part of the Cambridge standards, but I'm going to teach it because it shows up on questions. So my assumption is that they expect that you learned this in a prior life, like in an earlier chemistry class. But I'm going to teach it to you anyway. It is something that I do go over in the previous class. It's called the dilution of solution. So here's the topic. If I have this salt water, right, and I add water, what does that change? If I have some salt and I have some water, right, and I add more water, what happens? It changes the concentration, right? So adding water always decreases concentration. Doesn't change the actual amount of NaCl.
No.
The amount of moles would actually be the same. You have the same dissolve that you did after, but you're adding more solvent, which is you're adding more water. And so this is the solution that describes that relationship. It's M1V1 equals M2V2. You're going to use this whenever you need to go from a more concentrated solution to a less concentrated solution. So what you're actually going to be doing in next class's lab is that. You're going to be starting with a more concentrated starting solution, and then you're going to add water to get it up to this mark. And you're going to dilute the solution. That's what we're going to do as the first step of our lab next class. Let's continue. Practice question. How would we solve a dilution of solutions question? How many centimeters cubed of a 1 molarity MgSO4 solution must be diluted with water to prepare 250 centimeters cubed of aqueous 0.4 molarity MgSO4? Where would we start? Where do you start? We were looking for how much centimeters cubed of MgSO4 we need. That formula? Go ahead.
So you write in the formula.
Very good.
Right. So remember, this is before water,
Right, but how much do you have at the beginning?
and this is after water. You may want to write this down. When you're working with this formula, your initial amount, your initial molarity, and your initial volume is the amount before you've added water. So we have this information. It says we have the initial concentration. We don't know how many centimeters cubed we have of that initial concentration. So out of M1 and V1, which one do we have? M1 or V1? M1. And so you would put just the number
1.
1. You don't have to put in units because they always work out as long as you have centimeters cubed on both sides. E1, we leave that. That's our variable. We're looking for that. We don't know. what our initial amount is. It's asking for that, right? M2. Do I have M2?
0.4.
0.4. And our V2 is the amount that goes with 0.4, which is?
250.
Once you've plugged in all your numbers, then you solve for V1, which is 0.4 times 250. 0.4 times 250 is what? 100? Check that out. 250. 100 equals V1. And what's the unit for that? CM cubed. Match your units. If you start with CM cubed, you end with CM cubed. So, does that make sense? Does this process make sense? I have 100 centimeters of this more concentrated solution. When I add water, I have 250 centimeters cubed. So I add water, the volume goes up. When the volume goes up, what should happen to the concentration? When the volume goes up, the concentration goes down, right? That was the first thing we said here. Volume goes up, concentration goes down. Is that true? You start with a concentration of 1, you end with 0.4. Yes. Go ahead. All right, we have one more thing to cover before we're done for the day. So I have one more thing to cover that I've got to get through for us to do well in our lab next class. You need to be able to manipulate the concentration formula. So I'm going to skip the other dilution question. It is reviewed from pre-A, so there is a practice set up for you to do for it. This is the last topic that I'm going to cover today. There's another topic, but I'm going to wait for next class before the lab to do it. How do we use the concentration equation? So concentration equals moles over decimeters cubed. Oftentimes, you're going to have to use this equation with the moles equation. Do you remember what the moles equation is? Moles equals grams over molar mass. Many times you'll be asked for grams in questions, so oftentimes you'll have to use these two formulas together. So that's why I'm going to write them both out, because especially in the lab, there'll be a lot of times where you have to find the grams after you've found the moles. So write these two out, and let's take a look. And you'll see there's step 1, step 2 here to rearrange the equations. We're going to just take a look at some examples to see what we do. Do we have the formulas? Yes? All right, so let's at least take a look at 1 or 2 questions before we leave for the day. Remember, next class, short, pre-lab lesson, then we're going to go straight to the titration lab. Here we go. Calculate the concentration of the following solutions. A solution of sodium hydroxide. It contains 2 grams of sodium hydroxide in 50 centimeters cubed of solution. How would you calculate the concentration? What's concentration defined as? Moles over decimeters cubed. Do we have both the moles and the decimeters cubed right now? No. What do we have instead of moles? So step 1, change grams to? Well, how do we do that?
Divide the grams by the relative sum of mass.
Perfect. Or the molar mass.
Molar mass.
So we're going to start with moles equals grams over molar mass. We've got 2 grams told to us in the question. And what's the molar mass of sodium hydroxide? That's going to be the bottom number. So 2 on the top, molar mass on the bottom. You can get that by doing 23 plus 16 plus 1. Molar mass is
40.
40. 2 divided by 40 is
1 over 20 over 0.05.
0.05. That's our moles. Am I done?
No.
What do I now need to do? Step 2, find concentration. Concentration is defined as moles divided by VMQ. Write that down until you memorize it. And that is a formula, especially for the lab, that's all over the lab paper. How many moles do I have?
0.05.
How many decimeters cubed do I have?
0.05.
Perfect. That is the way you think about it. If you can remember what I told you in that lesson, remember, if I want to go from centimeters to decimeters, I got to move my decimal over one spot, but if it's cubed, I move it over 3 spots. And if you can just remember that, then you're just going to remember it's 0.05. So 0.05, and yes, a lot of times the numbers work out to be something simple. 0.05 divided by 0.05 is 1. And how would we write out that answer officially for Cambridge? Moles dm minus 3. The concentration is 1. Why 3?
Why minus?
Oh, to move decimeters cubed up for the unit, you change positive 3 to negative 3. Okay. That's just for writing the units out properly. That's how it's going to be presented to you in the lab. When they tell you a concentration, they're going to say it's 1 mole dm minus 3. That's how they're going to present it to you. So we just have to get comfortable with that writing of concentration. How I would have written it in the past is 1m in pre-A's. By the way, it means the same thing. Capital M is the same thing. Let's see if we can do one more. We got one more here. What will we do here? Calculate the number of moles of solute dissolved in the following. You've got 50 centimeters cubed of calcium hydroxide. You've got 0.01 molarity. What should we do? Formula for concentration. Start there. Concentration equal mole over EMQ. Okay. What do I have?
The concentration and the EMQ.
So 0.01 equals mole over
0.05.
0.05. Now what do I do to solve for moles? Multiply by 0.05. What's that? 0.05 times 0.01. What do you get?
0.005.
Yes, 0.0005. I get 3 zeros. Check to make sure. Are we okay with that? Manipulating the formula. Second part asks for mass. How would I get that? When I'm asked for mass, I'm always asked for grams.
Good afternoon, Golden Lines. This is
I'll
Emily
wait till
with
they're
your
done.
afternoon announcements. First, this is a reminder that tomorrow is PSAT for all 10th graders, and Friday is PSAT for all 11th graders. We will not be providing calculators, therefore you must bring your own 4-function or scientific calculator. You are not allowed to use a graphic or programmable calculator. Please be here on time. We will dismiss to our testing locations at 7:30. Again, all 10th graders, you're tomorrow. 11th graders and those with extended time, you are on Friday. Thank you.
All right, before leaving, let's wrap up this question.
Please remember to check your camera's email daily and report to school in proper CIA uniform. Make sure your outwear is solid white, black, or red. Also, please wear your student ID badge around your neck at all times. Detentions will be issued to students who do not adhere to the uniform policy.
I know where it is. Okay.
Please remember that you must wear your student ID every day. If you lost your ID, the cost for replacement is $5. If you receive a replacement ID, you must pay for it on OSP. Students who have unpaid balances will not be allowed to participate in field trips.
This is
Yearbooks are on sale now. They are $50 until October 31st. The price will rise afterwards. Buy your yearbook now to get a spot at the end of your signing party. Go to www.yearbooks@portercenter.com. Order number is 21027.